Since we revisited the natural logarithm, it's more than understandable that we will revisit the natural exponential function. And to start off with, we're interested in the number e. Now, e is a very important number in science and math. In fact, it has its own Wikipedia page right here. So it's called Euler's number. So it's a very important number. If it has its own Wikipedia page and it's this large and in charge, that's a sign that it's a big deal. Yes, a very big deal. Now, you can see right here at the top, they're defining E the way we're going to define it, which is not really how it's defined in algebra class. In algebra class, they're just kind of like, it's magic. There's a number that appears, right? But what is that number? Well, the area from underneath 1 over t, right? So the area underneath that 1 over t, which is the natural logarithm by definition. We just said so, right? So the area underneath that 1 over t curve from 1 to this magical number is 1. So in other words, that area is 1. So E is the number that makes that happen. E is the number that, hey, if I take the integral from 1 to this magic number of 1 over t. So in other words, I find this area underneath that curve, under the 1 over t curve, from 1 into this number, it will be equal to 1. So it is the number that such that the natural log of E is equal to 1. Interesting, huh? So it's a little mind-bendy. So it's this magical number that makes this area 1. No more, no less. That's what it is. So E is about 2.718. I mean, it's like pi. It goes on forever and ever with no pattern. So it's an irrational number. Cannot be written as a ratio. Cannot be written as a fraction. Right? It's an irrational number with no repeating pattern. Just like pi is. Or the square root of 2, that kind of thing. Okay, so that means that we can define e to the x, which, by the way, in computer code, a lot of computer programs don't like exponents, so they write it as this. So in computer programming, they'll write exp parentheses x. What that means is e to the x. They'll do it in several computer functions, where x is the natural log of y. Right? So e to the natural log of y, in other words, is, well, they actually wrote it right here. E to the natural log of x is x. In other words, e to the x and actually both of these two are saying the same thing. I'll write it out. These two phrases, the natural log of e to the x is x and e to the natural log of x is x, are coming from the fact that the natural log of x and e to the x are inverses of each other. If you remember inverse functions, if I make them y equals and y equals, are inverse functions. If you remember that from algebra class, right? So they reflect each other across the line y equals x. Matter of fact, I can prove it. If I grab decimals really quickly, it'll also be in here somewhere. It'll be part of the definition. There's even more ways to define e. So it's a fascinating number. So if I say y equals e to the x, and then I say y equals the natural log of x, and then just for fun, y equals x as a dotted line, you can see, hopefully, that the red curve and the blue curve, the natural log of x and the e to the x, are reflections of each other along that dashed line. They're inverses of each other. Right? Matter of fact, I can even draw that really quickly. So if I have, so I'm looking for my black pen, dotted line here. So if I have y equals e to the x right here, and then I have its compatriot, y equals the natural log of x. They're inverses. They're reflections along that diagonal line. Now, these properties are all, honestly, pre-algebra properties. We learned these before we even learned algebra. You just learned them with numbers. So these are pre-algebra power properties, right? That x plus y, e to the x, e to the y. Right? You learn them way back before you learn algebra, so like middle school, even earlier, when you learn like 2 to the 3 times 2 to the 5 is 2 to the 7, stuff like that. So e to the x times e to the y is e to the x plus y, e to the x divided by e to the y is e to the x minus y, and then e to the x to the power p is e to the x times p, where p is a rational number. Last but not least, the derivatives and integrals. So if I look on my derivative sheet, the derivative of e to the u is e to the u times u prime. So it's number 9 right here on the derivative sheet. And the integral of e to the something is e to the something. It's right here, e to the u. So that's number 6. I guess if I wanted to make this the same, I could use u for both of these. So this would be u and this would be u, right? Or if you like, u of x. So this was number 9 on the derivative sheet. And this was number 6, as a matter of fact, but on the integral sheet. The quick integral sheet. There's a larger integral sheet, which we haven't gotten to yet, but on the quick sheet, there you have it. All right, so let's apply that to a couple problems. So yet again, we're going to find a derivative and we're going to find an integral. Okay, so the derivative should be pretty straightforward. It's just a chain rule problem. So we have the derivative of e to the something. So the derivative of e to the something would be e to that same something. And then we multiply it by the derivative of the inside. So the next part to work on the x is the 20 and the sine. So the derivative of negative 20 sine is negative 20 cosine. Leave the x cubed alone. And then we finally will take the derivative of the innermost part, which is x cubed. So that would be 3x squared. So again, it's a double chain rule. It's like I want us to practice with that. All right, so derivative of the outside, that's the e to the something. So derivative of e to the something is just e to the something. Then the derivative of the next part, which is the negative 20 sine. The derivative of sine is cosine. So that's negative 20 cosine of x cubed. Then finally, the derivative of x cubed, which is 3x squared. Now, if I was going to simplify that, which they didn't ask me for, but if they wanted me to, it'd be negative 60 x squared cosine of x cubed times e to the negative 20 sine of x cubed. All right, now what about this one? Well, it's going to involve u substitution, of course, because it's the only trick we know. U would be the inner part, which would be 5x squared plus 9. Du then would be 10x dx. I don't want the 10x dx. I just want the x and the dx part. So I need 1/10 du is equal to x dx. So then what I'm taking is the integral of 1/10 in front e to the u du. But of course, the integral of e to the u is e to the u. It's everybody's favorite integral. So that would be 1/10 e to the u plus c, which would be 1/10 e to the 5x squared plus 9 plus c. Simple as that. Everybody loves e to the, because it's just the simplest derivative and integral there is.